Pipeline protocols overview. Selective repeat. Sender can have up to n unacknowledged packets in pipeline. RCVR sends individual acknowledgement for each packet. Sender that maintains timer for each unacknowledged packet. When timer expires, retransmit only that unacknowledged packet. Go back and sender can have up to n unacknowledged packets in pipeline. Receiver only sends cumulative ACK. It doesn't acknowledgement packet if there is a gap. Sender has a timer for oldest unacknowledged packet. When timer expires, retransmit all unacknowledged packets. Go back and sender. K-bit sequence, number in packet header, windows of up to n consecutive unacknowledged packets allowed. Here this one is the send base and this one is the next sequence number. Total n is the window size, and the green color that mentions the already acknowledged, and the yellow color that mentions sent not yet acknowledged, and blue color that mentions usable not yet sent, and white color that represents not usable. Acknowledgement of n acknowledgements all packets up to including sequence and cumulative ACK that may receive duplicates ACKs. See the receiver. Timer for oldest in flight unacknowledgement packet, timeout of n, retransmit packet n, and all higher sequence packets in window. GPN, sender extended FSM. This is the diagram that represents how the sender that extended with FSM. GPN, receiver extended FSM. Here corrupted data or out of order data packed. Discard don't buffer. Here no receiver buffering. Re-acknowledgement the packet with highest in order sequence number. Odd but simple. Acknowledgement for highest in order sequence number. Only need to remember. GPN in action. So this is the sender and receiver action that has been made while GPN transaction. Selective repeat. Receiver individually acknowledges all correctly received packets. Buffer packets as needed for eventually in order delivery to upper layer. Sender only resends packets for which ACK not received. Sender timer for each unacknowledged packet. Sender window n consecutive sequence numbers, limited sequence numbers of sent unacknowledged packets. Selective repeat. Sender receiver windows. Here green color that represents already acknowledged, yellow color that represents sent but not yet acknowledged, blue color that represents usable not yet sent, and white color that represents not usable. This is a sender view of sequence number, and in the receiver view of sequence number, pink color that represents out of order, that is buffered but already acknowledged, and ash color that represents expected not yet received, blue color that represents acceptable within the window, and white color that represents the not usable. In both n that represents the window size, both the receiver side as well as the sender side. Selective repeat. In sender side, data from above. If next available sequence number in window, send packet. Timeout of n, resend packet n, restart timer. Acknowledgement n in send base plus n minus 1. Mark packet n as received. If n smallest unacknowledged packet, advance window base to next unacknowledged sequence. Receiver packet n in receive base plus n minus 1. Send acknowledgement of n. Out of order, here buffer is out of order. In order, deliver, also deliver buffered in order packets. Advance window to next not yet received packet. Packet n in receive base is minus n, comma receive base is minus 1. Acknowledgement of n, otherwise ignore the packet. Selective repeat in action. Both the sender and receiver that sends the packets between them. Selective repeat dilemma. Example, sequence numbers 0, 1, 2, 3, window size is 3. Receiver sees no difference in two scenarios. Duplicate data that is accepted as new in what relationship between sequence number size and window size to avoid problem in B. Pipeline protocol summary. Selective repeat. Sender can have up to n unacknowledged packets in pipeline. Receiver sends individual acknowledgement for each packet. Sender maintains time for each unpackaged packet. When timer expires, retransmit only that unacknowledged packet. Go back and the sender that can have up to n unacknowledged packets in pipeline. Receiver only sends cumulative ACK. Doesn't acknowledgement packet if there is a gap. Sender has a timer for oldest unacknowledged packet. When timer expires, retransmit on all unacknowledged packets. TCP overview. This is a point-to-point protocol. One sender and one receiver. It is reliable in order byte stream. Here no message boundaries. In pipelined TCP congestion and flow control set window size. Full duplex data. Bidirectional data flow in same connection. MSS is a maximum segment size. And also it is a connection oriented handshaking, exchange of control messages in its sender receiver state before data exchange, flow controlled, sender will not overwhelm receiver. TCP segment structure, URG, urgent data that generally not allowed, ACK acknowledgement valid, PSK push data now generally that are not in used, RST, SYN, FIN, connection establishment, setup, tear down commands, internet checksum as in UDP. Here the destination port and source port as is in the UDP, and sequence number, acknowledgement number, counting by bytes of data, that is not segments, and receiver window URG data pointer. In receiver window, bytes receiver willing to accept, and URG data pointer pointing to the urgent code data. And TCP sequence number ACK, sequence numbers, byte stream, number of first byte in segments data, and acknowledgement sequence numbers of byte, next byte that is expected from the other side. Cumulative ACK. Question: how receiver handles out of order segments? A. TCP specification that doesn't say up to implementer. TCP sequence numbers acknowledgement. This is the simplest telnet scenario between the host A and the host B. TCP round trip time timeout. Question: how to send TCP timeout value? Too short. In premature timeout, unnecessary retransmissions. If it is too long, slow reaction to segment loss. TCP round trip time timeout. Question: how to set TCP timeout value? Too short, premature timeout, unnecessary retransmissions, too long, slow reaction to segment loss. It is longer than RTT, but RTT varies. Next question: how to establish RTT? It is a sample ERTT. It measured time from segment transmission until acknowledgement received. It ignores retransmissions. Sample ERTT will vary. That want to estimated RTT smoother. Average several region measurements, not just current sample ERTT. TCP round trip time and timeout. Estimated RTT is equal to 1 minus infinity into estimated RTT plus sample RTT, exponential weighted moving average, and the influence of past sample decreases exponentially past. Typical value is 0.125. This is the sample diagram that shows the TCP round trip time timeout, RTT and time in seconds. Round trip time timeout. This is the formula that is given to calculate the timeout interval. TCP reliable data transfer. TCP that creates RDT services on top of IPs, unreliable services. Pipeline segments, cumulative acknowledgements, single retransmission timer. Retransmission triggered by timeout events, duplicate acknowledgements. Let us initially consider simplified TCP sender to ignore duplicate acknowledgements, ignore flow control and congestion control. TCP center simplified. This is the diagram that represents the wait for an event for the TCP sender. Here data received from application above, create segment, segments number, next sequence number, and pass segment to IP. Timer currently not in running, next start timer, next sequence number is equal to next sequence number plus length of the data. Timeout divider, retransmit not yet acknowledged segment with the smallest sequence number. Start timer here. TCP sender events, data received from app, create segment with sequence number. Sequence number is a byte stream number of first data byte in segment. Start timer if not already running. Think of timer as for oldest unacknowledged segment, expiration interval, timeout interval, timeout. Retransmit segment that caused timeout. Start timer, acknowledgement received. If acknowledgements previously unacknowledged segments, update what is known to be acknowledged. Restart timer if there are still unacknowledged segments. This is simplified one. Next sequence number is equal to initial sequence number, send base is equal to initial sequence number. Loop forever, switch to the event. Event is data received from application above. It create a TCP segment with sequence number of next sequence number that pass segments to IP. If timer currently not in running, next start timer, next sequence number is equal to next sequence number plus length of the data. Here event, timer, timeout. Retransmit not yet acknowledged segment with the smallest sequence number. Start timer, event, acknowledgement received with acknowledgement field value of y. If y is greater than send base, then open the send base is equal to y. If there are currently not yet acknowledged segments, restart timer, else stop timer, then close the loop. Finally, end of the loop is forever. TCP retransmission scenarios, this is the last acknowledgement scenario between the host A and the host B. TCP retransmission scenario, the first diagram that represents the cumulative acknowledgement, the second one that represents the premature timeout between the host A and the host B. TCP center simplified. The data received from application above create send the segment data, and TCP sender not so simplified. Here data received from application above. So timeout interval is equal to estimated RTT plus 4 into d RTT. It creates segment sequence number, next sequence number that pass the segment to IP. Timer currently that are not running. Start timer, next sequence number is equal to next sequence number plus length of the data. Finally timeout. TCP's RDT versus GPN. Similarly, pipelined segments, cumulative acknowledgements, single retransmission timer, retransmission on timeout. Unique in TCP, timeout interval well defined. Only new acknowledgement refresh timer. Also unique in TCP, retransmit only one segment. Sending window is equal to one segment. Timeout interval doubled. Exponentially slow in case of back-to-back timeout events. TCP RDT versus GPN. Here similarly, the similarity is pipelined segments, cumulative acknowledgements, single retransmission timer, retransmission on timeout. Unique in TCP, timeout interval well defined, only new acknowledgement refresh timer, and then also unique in TCP, retransmit only one segment, sending window is equal to one segment, timeout interval doubled, exponentially slow in case of back-to-back timeout events, more that being used uniquely in the TCP. It has the delayed acknowledgement and also fast retransmission. TCP acknowledgement generation, event at the receiver, TCP receiver action. It's in event at receiver, arrival of in order segment with expected sequence number, all data up to expected sequence number that already acknowledged. Arrival of in order segment with expected sequence number, one other segment that has acknowledged pending. Arrival out of order segment that is higher than the expected sequence number, gap detected. Arrival of segment that partially or completed filled by gas. In TCP receiver action, delayed acknowledgement, wait up to 500 milliseconds for next segment. If no next segment, send acknowledgement. Immediately send single cumulative ACK, acknowledging both in order of segments. Immediately send duplicate acknowledgements that indicating sequence number of next expected byte. TCP acknowledgement generation, in evented receiver, arrival of in order segment with the expected sequence number, all data up to expected sequence number that is already acknowledged. Arrival of in order segment with the expected sequence, here one other segment that has acknowledged pending. Arrival out of order segment that is higher than the sequence number, gap deducted. Arrival of segment that partially or completed fill gas. In TCP receiver action, delayed acknowledgement, wait up to 500 ms for the next segment. If no next segment, send acknowledgement. Immediately send single cumulative acknowledgement and acknowledging both in order of segments. Immediately send duplicate acknowledgement that indicating sequence of next expected byte. TCPs, RDTs versus GPN. It also in unique TCP. Here retransmit only one segment. Sending window is equal to one segment. Timeout interval doubled. Exponentially slow in case of back-to-back timeout events. In more being unique in TCP, delayed acknowledgement, receiver buffer, out of order packets, fast retransmission. TCP fast retransmit, timeout period often relatively long, long delay before resending lost packets. Detect lost segments via duplicate ACKs. Send often, sends many segments back to back. If segment is lost, there will likely be many duplicate acknowledgements. TCP fast retransmit after sender receipt of triple duplicate acknowledgement. Fast retransmit algorithm, event acknowledgement received with acknowledgement filled value of y if y greater than send base is equal to y. If there are currently not yet acknowledged segments, restart timer, else stop timer, else increment count of duplicate acknowledgement received for y if count of duplicate acknowledgements received for y is equal to 3. Then resend segment with the sequence number y, count of duplicate acknowledgement is equal to 0. TCP flow control. In flow control, receiver control sender. So sender won't overflow receivers buffer by transmitting too much too fast. TCP flow control, receiver advertises free buffer space by including round value in TCP header of receiver to sender segments. Receiver buffer size set via socket options. Typically default is 4096 bytes. So many operating systems auto adjust received buffer. Sender limits amount of unacknowledged in-flight data to receive round value. Guarantees receive buffer will not overflow. This is the receiver side buffer. Connection management. Before exchanging data, sender and receiver handshake. Agree to establish connection, each knowing the order that willing to establish connection. Agree on connection parameters. TCP three-way handshaking from the client side to the server side, ESTA-B and then ESTA-A. TCP closing a connection, client server each close their side of connection. Send TCP segment with fin bit is equal to 1 that respond to the received fin with acknowledgement. On receiving fin, acknowledgement that can be combined with own fin. Simultaneous fin exchanges that can be handled. TCP closing a connection from the server side to the client side to the server side. Principles of congestion control. Congestion. Informally, too many sources sending too much of data too fast for network to handle. It is different from flow control. Main frustrations, lost packets, buffer overflow at routers, long delays, queuing in router buffers. Here it has a top 10 problems. Causes, cost of congestion scenario. 1. 2 senders, 2 receivers. Output link capacity or 1 router, infinite buffers. Here no bit error and also no retransmission. Causes cost of congestion scenario 2, no router, finite buffers, sender retransmission of timed out packet, application layer input is equal to application layer output, transport layer input which includes the retransmissions. Causes cost of congestion scenario 2, idealization, perfect knowledge. Sender sends only when the router buffers available. And idealization known loss, packets that can be lost, dropped at router due to full buffers. Sender only resends if packet known that to be lost. Idealization known loss, packets that can be lost, dropped out route due to full buffers. Sender only resends if packet known that to be lost. Realistic, duplicates, packets that can be lost, dropped at router due to full buffers. Sender timers out prematurely, sending 2 copies both of which are delivered. Realistic duplicates, packets that can be lost, dropped at router due to full buffers. Sender times out prematurely, sending 2 copies both of which are delivered. Cost of congestion, more work, retransfer given good put. Unneeded retransmissions, link carries multiple copies of packet, also decreasing good put. And causes cost congestion scenario 3, 4 senders, multi-hop paths, timeout as well as retransmit. Another cost of congestion, when packet dropped, any upstream transmission capacity used for the packet that was wasted. Approaches congestion control end to end. In end-to-end systems, infer congestion from observed loss delay. No explicit feedback from network, that is routers. End system, infer available rate / bandwidth by trying and failing. Approach taken by TCP. Network assist. Routers that provide feedback to end systems from observed queue size, free buffer space, single bit in packet that indicating congestion. Example TCP, IP and ACN. Routers tells explicit rate, sender sends at the rate. TCP congestion avoidance, AMD, it approaches sender increases retransmission data window size until loss occurs. Additive increase, it increases CWND by 1 MSS every RTT until loss detected. Multiplicative decrease, cut CWNT in half after loss. CWNT TCP sender limits. CWND is dynamic function of perceived network congestion, and TCP sending rate roughly sends CWND bytes, waits RTT for acknowledgements, then send another CWNDT. TCP initialization slow start. When connection begins, increase CWNT exponentially until first loss event. Initially CWNT is equal to 1 MSS, double CWND every RTT, done by incrementing CWND for every acknowledgement received. Here summary is, initial rate is slow but ramps up exponentially fast. DCP deducting, reacting to loss. Loss indicated by timeout, CWNDT set to 1 MSS. Window then grows exponentially as in slow start to the threshold, then grows linearly. Loss indicated by 3 duplicate ACKs, TCP Reno. Duplicate acknowledgement indicates network that is capable of delivering some segments. CWNDT is cut in half window, then grown linearly. This is the TCP switching from SS to CA. Switching from SS to CA, the question that arises, when should the exponential increase switch to linear? The answer is when CWND gets to SSS threshold. Implementation, variable SS threshold. On loss event, SS threshold is set to half of CWNDT just before loss event. Summary, this is a TCP congestion control. Slow start and then finally we will get the congestion avoidance. Summary, TCP congestion, slow start, congestion avoidance. full TCP congestion control, from slow start, congestion avoidance, finally we get the fast recovery. TCP features: TCP over long fat pipes, example 1500 byte segments, 100 ms RTT, want 10 Gbps throughput. The rate that requires 83,333 in flight segments. TCP throughput with loss: average TCP throughput as a function of window size RTT. Ignore slow start. Assume always that data to be sent. W window size that is measured in bytes where loss occurs. Average window size in flight in bytes is 3/4 of the W, and average throughput is 3/4 W per hour 3 TW. Average throughput equal to W by bytes per seconds. And long for pipes, throughput in terms segment loss probability L. TCP throughput MSS is equal to 1.2 divided by RTT of root of L. TCP fairness. Fairness the goal of the fairness: if k TCP sessions share common same bottleneck link of bandwidth R, each should have average rate of R by k. Why is TCP fair? Two competing sessions. Additive increase gives slope of 1 as throughout increases. Multiplicative decrease decreases the throughput proportionally. Fairness more. Fairness and UDP. Multimedia apps that often do not use TCP do not want rate throttled by congestion control. Instead use UDP. Send audio/video at constant rate. Tolerate packet loss. Fairness parallel TCP connections. Application that can open multiple parallel connections between two hosts. Web browsers do this. Example: link of rate R with the existing connections. Never app ask for one TCP that gets rate R divided n. Never app ask for 9 TCPs gets R by 2. Approaches congestion control end to end. In end to end system, infer congestion from observed loss, delay. No explicit feedback from network routers. End systems interference available rate per bandwidth by trying and failing. Approach that is taken by TCP. Network assist. Routers provide feedback to end systems from observed queue size, free buffer space, single bit in packet that indicating congestion. TCP IP is n. Routers tells explicit rate. The sender sensors the rate. Explicit congestion notification is n. Network assisted congestion control. 2 bits in IP header TOS field that is marked by network router to indicate congestion. Congestion indication that is carried to receiver host in receiving host. Explicit congestion notification. Network assisted congestion control. Receiver sets ECE bit on receiver to sender. Acknowledgement send to notify sender of congestion. Sender sets CWR bit on sender to receiver. Data segment to confirm CWND being reduced. TCP segment structure. Source port, destination port, sequence number, acknowledgement number, and checksum, receiver window, URG data pointer, options with variable length, application data with variable length.